Good morning, class. So today we're just going to go over homework 8, which is a homework about bipolar transistors. And the reason we did homework 8 is because you're going to have a quiz on Wednesday on bipolar transistors. So I felt that you should have at least one homework on it before the quiz. So if we draw our bipolar transistor, okay. Just move it over some room. All right, this is the emitter, which is, we're doing an NPN. This is the base, which is P-type, and the collector, which is N-type. And we're going to put it in the active region. And so in the active region, we're going to forward bias the base emitter junction. And remember your mnemonic: to forward bias, you put a positive voltage on the P side. Okay. All right. And so let's sort of do this in stages. So when you forward bias the junction, what you've been taught is that the injected carrier density of electrons injected into the p-type base goes as n b naught e to the e, the forward bias, which is the base emitter voltage, divided by kT. And if we did have the collector over there, you've learned that the solution would be, something like that, where this would go to NV0. And that would go as e to the minus x over L. Now, so we're going to reverse bias the base collector junction. And so that means putting a positive voltage on the inside to reverse bias. Okay, and now you've been taught this a couple of ways. I mean, one way is to think of, this reverse bias junction as like a vacuum cleaner. And so instead of having our exponential it just goes like a straight line down to 0. And the other way to think about it is that whether a PN junction is forward or reverse bias, okay, the in this case not injected carrier density is going to go as NB0. Now think about it, e to the forward bias. The forward bias would be the base with respect to collector. Okay, but this is, VCB, right? The voltage of the collector with respect to the base, so that's negative, which because it's reverse bias. And so e to the minus a reverse bias is a small number, and so we approximate it as 0. So either way you think about it, it goes to 0 there, and it's this value here. Okay, and up till now we just sort of left it at that you can sort of just approximate this as a straight line, and so you can get the current through Fick's law and all that stuff. All right, but the homework problem is meant to sort of step back from this and realize that, okay, whatever this distribution is of the injected carrier density, it has to obey diffusion theory. Now, diffusion theory, going back over that, you know what that is. Diffusion theory is that minus dF, where F is the flux, dx. All right. Now I'm not going to go all the way back over diffusion theory, but remember what dF dx means. That means the change in flux. Flux is carriers per unit area per unit time. And so if this is changing, okay, the carrier's got to go somewhere because the flux is changing. And so, you know, what you've learned is that that's equal to the disappearance rate of carriers, which is n over the recombination time. So this represents, as you move through x, the flux changes, okay, and since the flux is changing, those carriers, and so if the flux is changing, now, okay, let's think about that a little bit. What that has to mean is that this thing is not exactly straight, all right, it has a very, very slight curvature to it. All right, so that F, now remember what F is minus d dp dx. So that's the flux as I move through here. That's slowly getting a little bit smaller, okay? And so since it's getting a little bit smaller, those carriers are disappearing, and they're disappearing because they're recombining according to, sorry, n minus n b0 over tau. That is, any n above nb0 has to be going away. And so if we continue to write that and we plug in there, we get that d squared t dx squared is equal to, oops, not t, n, d squared n dx squared is equal to n minus nb0 over tau. And rewriting that, that's d squared n dx squared is equal to n minus nb0 over d tau. And we define that then d tau as L squared. So the problem is for you to realize that, well, okay, we approximated this as a straight line, but in fact it has to obey this differential equation because it has to obey diffusion theory. And for you to go through the process of figuring out what n of x actually is. All right, and you know, since n of x obeys this equation, the solution for n of x has to be, and I gave it to you in the solution and the problem. Okay. Now we're used to just seeing this one here because it's decaying, but I mean both the growing and decaying are solutions to the differential equation, and you can see that by taking the second derivative. Then, okay, when you take one derivative, you get a 1 over L, you get a minus 1 over L, and then you take the derivative again, you get an L and a minus 1 over L. So that becomes A over L squared e to the x over L plus b over L squared e to the negative x over L. All right, if you look at that, that's n minus nb0 over L squared. And so hopefully when you did, as you did the problem, you checked to make sure that that actually was a solution as suggested. All right, so that's the solution. We just have to find A and B. and find A and B, we use our boundary conditions, okay? And as suggested in the problem, I'm going to just write that as n sub 1 so that I'm not carrying around all these variables. Okay, and so n of 0 is n1, and that's equal to nb0 plus a plus b, plugging in x equals 0 in there. So that's our one boundary condition. And our other boundary condition is n of xb, right? This is x sub b is 0, and that's equal to nb0 plus a e to the xb over L plus b e to the minus xb over L. Checking my focus here, and I'm out of focus. Okay. I don't know what to do to make it go into focus. All right, it's in focus. I don't want to screw it with it anymore. I'm sorry about that. I continue to be bedeviled by this camera not wanting to focus properly. All right, so let's go back over this. This is a solution. I gave that to you in the problem. You could have checked that by taking the second derivative and showing that it's equal to that, and so it satisfies the fusion theory. And then to find A and B, you use the boundary condition, n of 0, and these two are the boundary conditions. All right, the rest is algebra. You know, I once had a professor who told me that physicists tend to be good at algebra because they have to do it so much. But anyway, if you got to this point, okay, you've set up the problem, which is, you know, sort of half the battle. All right, so let's do algebra. So to do algebra, we want to take this, I mean, you know, it's the usual thing, two equations, two unknowns, and so sort of the simplest way is to get rid of one of the variables. And so, I mean, the way I usually do something like this is that I multiply, like one of the equations, 0 times e to the xb over L, and I multiply e to the xb over L by both sides. So that's 0, of course. And so this is nb 0 e to the xb over L plus a e to the 2 xb over L plus b. And you know, the reason why I did that is now I can subtract this one from that one and get rid of b. So if I do that, if I take that minus that, that's n1, okay, nb0 times 1 minus e to the xb over L plus, now that the b goes away, a times 1 minus e to the 2 xb over L and so you can sort of see that I can easily solve for a then. A is equal to n1 minus nb0 that over there and dividing by 1 minus e to 2xb over L. And you would do a similar thing to solve. You could take A and use one of these to solve for B. Just checking my focus. And my focus is still okay. Oh, God. But it's sort of, I mean, sort of easier that rather to do the same thing. Take this equation here and multiply it times e to the minus xb over L to get rid of that, and then do the same thing over here. And so you would find that B is equal to n1 minus n0 times 1 minus e to the negative xb over L over 1 minus e to the negative 2xb over L. And that's it. Okay, that's what I asked you to do. Now, what I'm going to do next, let's see what the best way to do this is. Let's put it over here. We know diffusion theory now. So let's write our answer over here. A is equal to n1 minus nb0 times 1 minus e to the xb over L over 1 minus e to the 2 xb over L, and B is equal to n1 minus nb0 times 1 minus e to the negative xb over L over 1 minus e to the negative 2 xb over L. Okay, where, let's just write down n is equal to n b0 plus a e to the x over L plus b e to the minus x over L. Okay. And now I can erase this over here and start looking at this answer and thinking about it. All right, so I didn't ask you to do this, but you know, the solution looks, you know, not so friendly. I asked you to do some approximations for small values and stuff, but I wanted to show you. I didn't ask you to do this. Now, what is a plus b? Well, we erased it, but remember n1, write it down here, n1 is equal to nb0 plus a plus b, because that's the solution at x equals 0. All right, and so sort of a fun thing to do if you like doing algebra is to show that that is equal to that. Okay, so let's go ahead and do that. All right, so let's write it out. N1. I'm going to start using shorthand, just N0, because lowering the amount of things I have to write. Okay. Oops. Okay, so that's A and B. then that's b. So what do? Well, you know what to do here. You put it under a common denominator. Okay, and when you do that, if you write that, okay, so you have to put that one there. All right, plus n1 minus n0 and that's that one over there. Cat. Okay, and now you just sort of look at it and start collecting variables. You know, the way what you do here is okay, you can sort of do it in steps. If you take n1 first, okay, well, let's do n0 first. Let's do n1. So n1, okay, n1 times that, 1 minus e to the negative 2 xb over L, okay, plus 1 minus e to the 2 xb over L, right? Okay, and then n0 minus n0. Okay, now let's multiply it out. Okay, so that's 1 minus e to the negative xb over L. Okay, minus e to the negative 2 xb over L. All right, plus e to the oops, I made a mistake here. That should be a plus. Yeah, that should be a plus there. That's A. Sorry, and that's B. Okay, all right, yeah, because that one has to go away. Plus e to the negative xb over L. And what you see is these two are going to cancel out. And then let's do a minus n0. Okay, this one here, so that's 1. Now let me fix that. Okay, 1 minus e to the negative xb over L minus e to the 2 xb over L. And I need to fix that there. Okay, and then plus e to the xb over L. All right, and you see that cancels that, and that cancels that. That's over our denominator. Okay, and so if you collect variables, you see that's n1. Now I'm going to write that out. 1 2 minus e to the negative 2 xb over L minus e to the 2 xb over L. All right, minus n0. okay, and that's 2 minus, that should be 2. Right, minus e to the negative 2xb over L minus e to the 2xb over L over our denominator. And you see they're the same thing. So that's n1 minus n naught times 2 minus e to the negative 2xb over L minus e to the 2xb over L. Now, I've been just doing our denominator. Okay, so now doing our denominator, that's 1 minus e to the 2xb over L minus e to the negative 2xb over L plus 1, and you're in focus. All right, and if you look, this is n1 minus n0, and it works. Okay, so that was just to show you that that all this is correct, that those A and B values give you the correct boundary conditions when you plug them in, particularly at x equals 0. You could do the same thing at x equals xb, and you would show that they work. All right, so now the fun part. Let's take our solution and have a look at it. All right, so the first thing I wanted you to do, I asked you to do, is I said, okay, make the base really big. All right, you know what's going to happen then if the base is really big. It's like that base collector junction just goes away, and it goes back to our simple single junction solution. And so if xb is much bigger than the diffusion length, all right, well, you can just look at that. So A, okay, this is going to start dominating. So that's n1 plus nb0 e to the xb over L, because that's now much bigger than 1, over negative e to the 2 xb over L. All right, and if you look at this, that's, you know, the square of something big, so that's going to become 0. B for xb is much bigger than L. All right, n1. Now, that is e to the minus a big number, so it goes away. So this just becomes nb0. And that's 1. So it's just n1 minus nb0. And our solution then is n of x for xb is much bigger than L becomes, okay, A is 0, so that one goes away. Where's our solution? Here. nb0 plus b n1 minus nb0 e to the negative x over L. And this is our single junction solution. So you see that it correctly reverts to the single junction solution. Remember, I won't draw here, but I'll sort of just indicate it, which is e to the minus x asymptoting to nb0, which is what we had erased before. See, when x goes to infinity, that goes away, it becomes nb0. When x is 0, that cancels that and becomes n1. So it does what it's supposed to do. All right. So next comes the real fun part, which is to plug in values. So now what I did was I said, okay, let's take some intermediate kind of ring. Let's make that equal to the diffusion length L. Now, that's kind of if you think about it, well, when we go back over it, when we get the solution, that's kind of a bad design if you think about it, because it sort of means that a diffusion length is the length over which carriers disappear. You don't want any carriers to disappear. And so, this would be sort of a bad design. You want XB to be smaller than that. But I just did it because that makes it sort of easier to plug in stuff. All right, and if you plug in then, okay, so let's just do it. A then is equal to N1 minus NB0 times 1 minus, if XB is equal to L, that's just E. Okay, so don't get confused, that's not the electronic charge, it's Euler's constant. All right, and 1 minus E squared. And if you work that out, and you plug in numbers, all right, so I'm going to write it out this way. Since E squared is bigger than 1, this becomes negative. I told you to do it to 4 significant digits. 1565. Okay, so that's 1 over that times N1 minus 1 minus E is a minus sign, so that becomes positive 1.718 NB0. And B is equal to N1 minus NB0. Now this is 1 minus 1 over E, and then this is 1 minus 1 over E squared. And if you work that out, that becomes 1.1565 times N1 minus 0.632 NB0. And you sort of see that things are working out because you see that that A plus B is going to be N1. Look at it, A plus B, that's going to be N1. Well, you have to multiply those together, but you'll see that then that's equal to minus NB0, and so the solution works. And what I told you to do was to use a value. So basically, make that 100. Now, what would it have to be 100? Well, I haven't worked it out, but VBE doesn't have to be very much then. But I chose 100 because I wanted you to be able to see things on a linear scale. So make N1 equal to 100 NB0. And if you plug that in then, okay, then A, if this is 100 NB0, all right, that becomes minus 15.919. And B, if you plug in 100 NB0 here, all right, and you have to use enough digits to make this work out right, or to be able to add right. 114.919 NB0. And you see again that if you take A plus B, you get N1 minus NB0 because that's 99. Okay, and I said to plot it. Okay, so let's write out the equation then. So N of X is then equal to NB0 minus 15.919, and what I'll do is let me just bring the NB0 out. Right. And I told you to plot it. Okay, and so, just checking my focus. If you plot that, okay, now unfortunately, I'm not multimedia here, so I can't bring it in. I can, maybe, I don't know if this will work, show you what the plot looks like. All right, I'll be handing out the solution. I was worried that was going to screw up my focus completely. But let's go ahead and, so I told you to plot it versus x over xb. So the plot goes from 0 to 1. And I told you to plot n over nb0. So that starts at 100. Right? Because n1 is 100, nb0. And if you plot it, I mean, it. Okay, let's do it this way. Let's see if I can make a straight line. All right, and what you sort of see is that it kind of bends down and goes like that, which I did a horrible job of doing that because it's really smooth. Okay, but you, if you plotted it, which you're supposed to do so you can see this, it's very close to a straight line, but it starts out with a little bit higher slope and then it goes down. All right, and the final thing, okay, so what you see is that it starts out with a higher slope and then goes to a lower slope. Now, why is that? Okay, because carriers are being lost in the base. Remember, this is JEN, and this is alpha JEN over here, where alpha is slightly smaller than 1. All right, this is JEN over here. That's slope, right? I mean, well, it's proportional to that slope. And alpha JEN is proportional to that slope over there. So, so alpha JEN over JEN, which is alpha, is equal to, pardon me, is equal to dN dx evaluated at x equals xb over dN dx evaluated at x equals 0. So that's our base transport factor, alpha. All right, well, dN dx, I mean, you can work it out. Okay, dN dx is just taking this derivative. So, let me write it out here. So n prime is equal to, okay, this term goes away, so that becomes minus 15.919 over L, e to the x over L, just taking its derivative, minus 114.919 over L e to the negative x over L. And so this ratio then is simply plugging in. The L's go away, so this becomes minus 15.919 e to the xb over L minus 114.919 e to the negative xb over L over, that's 1 now. And this is 1. Okay, and I gotta flip here. So alpha then is equal to, just taking E times that. The minus signs all cancel out. So you get 43.272 plus 42.276 over 130.838. So that's equal to 0.654. Okay, so that's the final answer. And basically, you could have considered this to be an overall exercise to determine what alpha is for an NPN a transistor designed with the base width equal to the diffusion length L. So I hope that you learned from this homework assignment. It reinforced your understanding of the fact that this distribution here is not exactly linear. It's close to linear. Hopefully you were able to plot it, and you saw that it was pretty close to a straight line. Even though, all right, by diffusion theory, it has to be the sum of two exponents. So it's pretty interesting, actually, that when you do all this and you solve for the boundary conditions, the sum of a constant and two exponents can look very much like a straight line. But now you know that even though we've approximated it as a straight line, underlying it is this solution, just with A and B, such that it gives you approximately straight line. And the result of it is, it just all works out that it's almost a straight line, but with a slope that's slightly going down. Actually, it goes down, for xb equal to L, it goes down by quite a bit. All right, an alpha of only 0.65 would be a pretty poor transistor if you think about it. So, from this you've also learned that in order to make a good transistor, you want xb to be pretty much smaller than diffusion length L. Diffusion lengths maybe, might be on the order of a micron, and so you want that to be much smaller than a micron. Okay, so that's it. That's it for this lecture. We just went over homework 8, and Wednesday during the chat class time we'll have a quiz like we did for diodes a few weeks ago. Okay, that's it.